Full fine-tuning may waste memory, while QLoRA can trade speed for fit. Compare VRAM, throughput, and quality to choose the right adaptation path before training. You'll compare full fine-tuning, LoRa, and QLoRA with a decision matrix that returns the fitting choice. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Most teams face the same question when they need a tuned model for a domain. Do you update every weight, add a tiny adapter, or compress to low precision and tune there? The choice changes how many GPUs you need, how long training takes, and how close the model gets to your target quality. I'll show a planning workflow so you decide before you click train. At a glance, full fine-tuning means updating all parameters. LoRa means adding small low-rank adapters, so you only train a few new matrices. QLoRA is about operating in 4-bit storage and tuning with quantized optimization to save VRAM at some throughput cost. Each option trades memory, speed, and capacity differently. We will build a small planner that estimates adapter size, converts that to GPU needs, applies a quality gate, explores adapter rank, and then outputs a compact decision matrix you can paste beside experiment logs. That gives you an actionable method selection before committing time or money. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Start by estimating how many trainable parameters a LoRa adapter would add, so you can budget checkpoints and GPU memory. This snippet estimates the trainable LoRa adapter size for a 7B model, giving you a concrete number to budget for checkpoints and memory. Full fine-tuning updates every parameter, but LoRa only adds small, low-rank matrices to selected projection sites. The variables, layers, hidden, rank, and LoRa sites make the assumption visible instead of hiding it in a config file. Increasing rank grows LoRa params linearly, so it can improve adapter capacity while also raising memory and checkpoint size. The visible output shows the adapter scale and trainable share, which is the first sanity check before budgeting GPUs. Next, turn those parameter counts into a memory gate so you can see what fits on one GPU and what forces model parallelism. This example converts the earlier parameter counts into a rough GPU memory gate so you can rule options in or out fast. Teams often discover too late that full fine-tuning is not a budget problem. It is a feasibility problem. The VRAM dictionary separates full, LoRa, and QLoRA using simple byte assumptions for trainable state and frozen model storage. The byte math is a planning estimate, not a replacement for a profiler during real training. The visible output shows which methods fit a 24 GB budget and which one is cheapest, so the run plan can fail fast. Fitting memory is necessary but not sufficient, so add a simple evaluation gate that keeps only methods which meet your quality bar and then prefers throughput. This code adds an evaluation gate so you don't pick a method that fits memory but fails quality. A method that fits the GPU can still miss the required quality, so quality and TOC-S are kept as separate measured run metrics. The eligible list filters out methods that either exceed budget GB or fall below need quality. Then Max chooses the fastest remaining method, which mirrors how experiment tracking often turns many runs into one decision. The visible output shows the selected method, its quality, and throughput, linking engineering budget to the model result. Adapters are tunable. Treat rank as a capacity knob and pick the smallest rank that meets validation, not the biggest by default. This snippet treats rank as a tunable capacity knob and helps you pick sensibly, not by habit. The helper adapter params 4 recalculates adapter size for each candidate in ranks, and rank GB turns that into a fit check. Q by rank is a compact planning curve for the demo, representing measured validation quality you would normally log from real runs. Higher rank increases adapter capacity and memory together, so the safest choice is the best quality among safe ranks, not simply the largest number available. The visible output shows the chosen rank and its estimated run size, making the trade-off explicit. Finally, collapse budget, quality, throughput, and checkpoint footprint into a small decision matrix you can store with your experiment run metadata. This example brings the budget, quality, throughput, and checkpoint size into one small decision matrix you can actually use. The rows tuples keep each method comparable: method name, estimated memory, checkpoint size, quality, and throughput. Valid removes choices do not fit budget GB or need quality. And winner picks the fastest survivor while preferring lower memory on ties. This is intentionally small enough to paste beside real experiment tracker exports. The visible output shows the final method, checkpoint footprint, and throughput score, which is the baseline decision before launching training. You can map this toy workflow into a real project by swapping the toy quality curve with actual validation runs on your domain dataset and exporting those numbers into the same rows structure. That makes the decision matrix a live dashboard for your tuning experiments. Use this pattern when you must pick an adaptation path before expensive runs start. Use full fine-tuning if you can afford the GPUs and need the absolute best fit. Use LoRA when you need small checkpoints and fast iteration. Use QLoRA when VRAM is the hard limit and you accept some throughput cost. One caveat: these are planning estimates. Always validate with a short real run and a profiler. Tune the adapter rank against your domain validation split and rerun the decision matrix with actual measured throughput and quality. Focus on the smallest rank that reaches your need quality on that dataset, while staying under your budget GB. If practical AI engineering helps, subscribe and watch the AI engineering videos.